So on this lecture, we're just going to talk about momentum. Okay, so now we want to look at relativistic momentum right here. And why, so we brought up momentum in classical mechanics when we got to collisions. Why? Why do we bring up momentum for that? If we just have two objects colliding, this one's going that way and this one going this way, why didn't we use forces right here? Well, because the force when two objects collide depends on how squishable it is. It depends on the squishability, and every object has a different amount of squishability, which made it very difficult right there. So if we tried to use forces, we'd have to look at squishability. We don't want to. If we go back to Newton's second law, which is what? When you add up all the forces. Now, it's not really MA. That's not really what Newton said. What Newton said was the sum of the forces is the change in the momentum. That's what he really said, dt. Where the definition of momentum, we said, was mv. Or I should say, since we're talking about within the frame, we shouldn't use v anymore. Remember, that was only the speed between Frank and Mary. Maybe we should use u now. So this is really the derivative with respect to time of mu. Now, if m is a constant, then you can bring it out in front and you get ma. So you get F equals ma, but that's only true when m is a constant. But what he said was this right here. Now, if we call this object A and this object B, if we look at Newton's third law, that is, for every action, the force on A due to B is equal and opposite to the force on B back on A, which is minus the force on B back on A. So for every action, there's an equal and opposite reaction. So if we ask for the force on the entire system, some of the forces on the entire system, well, that always better be zero, because for every action, you're also going to get a negative reaction. When you add them up, you're always going to get zero. So this is true for any system, as long as you include everything that's affecting it. Well, if this is zero, that means that this right here, the change in the momentum of the system better be zero with respect to time. Well, we know the derivative is equal to zero when this is a constant. So that implies that the momentum of a system is a constant right here. Which is nice, and that's what we used in classical mechanics, that all the MVs before the collision equals all the MVs after the collision. And on that first homework assignment, we also showed that if it's conserved in Frank's frame, it's conserved in Mary's frame. But remember, we weren't using the Lorentz transformation. We were using the Galilean transformation. So, is momentum still going to be conserved in both frames, or is it even going to be conserved at all, even in one frame, now that we have different equations here? So let's see right here. So what we're going to do is we're going to have, let's say we have Mary moving along. When I draw the axis, Mary, remember she gets bent in, but that's only on an XCT plot. On an XY plot, it's always perpendicular right here. So there's my Mary, except I should make her in red because Mary's always in red. So we put Mary in here. Remember, she's moving along this way with a velocity v, so this is Mary. And then we have Frank. Also, I'll put Frank right here. So there is Frank. Okay, and Mary is just going to grab a ball and throw it straight down. Now, this is out in space, right? There's no gravity to this. This could be 2 rockets or whatever. There's no gravity here. So she's just going to throw it down relative to herself. She's just going to throw it straight down at a speed u naught. Well, minus u naught because it's going down. So her u naught y prime, the speed that she throws it down, is minus u naught. Now, Frank is just going to throw the ball exactly the same as identical ball, throw one straight upward with a speed u naught. So now from you notice right here, and they're going to collide. This one's going to come down, it's going to collide with the one going up. Now we have to be a little careful here because there's a lot going on in this problem. You know, you've got 2 different perspectives. You got Frank's perspective and you got Mary's perspective. You got Mary's ball and you got Frank's ball. You also got the X motion and the Y motion for each one. And you also have before the collision and after the collision. So we have to really be careful right here about how we handle this so we can do it all without getting mixed up with all this nomenclature. So what we'll do is we'll look at it just from Frank's perspective, not from Mary's perspective. So this is all going to be done from Frank's perspective. Now Frank, even though Mary threw the ball straight down, since she has a velocity this way at v, Frank's going to actually see the ball not go straight down. He's going to actually see it come in at some angle like this, right here. And then it's going to come down, run into his right there. And then he's going to Mary, the ball's just going to come right back up to her. But not to Frank, it's going to go off like this, right here. And so by the time Mary catches the ball, she'll be over here someplace. So here was Mary when she caught the ball. So that's all Mary did was just throw it straight down. All Frank did was throw it straight up. If you looked at it from Mary's perspective, she would have said, no, I just threw it straight down. Frank is moving this way, right there. And so I would have seen, when you threw it down, I would have seen Frank over here, and you would have seen it the other way, right there. But we're just looking at it from Frank's perspective, right there. Okay, so now we want to do is we want to look at it before the collision and afterwards. So again, well, right here, this will be before the collision, and over here, this will be after. So we can keep it straight right there. And we want to get the change because we want to see if the momentum changes or not. So over here, we'll call this the change in momentum. Change in momentum. Because we know that for the entire system, it better not change. It's a constant, so there better not be any change right there. Now, we also have Frank's ball and Mary's ball. So right here, this will make this Frank's, going that way, Frank's. And down here, this will be Mary's. Frank's. Okay, and then we have, within that, we have the X and the Y. So we have X and the Y for Frank's, and we have the X and the Y for Mary. Okay, so before we do, we get the momentum. Remember, the definition of momentum is right there. Why don't we get the velocity? First of all, what is Frank's X velocity right here? Well, Frank is just throwing it straight up. He has no X velocity, so U naught X is equal to 0. That means his momentum right here in the X direction, P of Frank in the X before, this is all before, is also equal to 0. Okay, and then what does he see the ball do after it hits this? It comes straight back down to him. So he just sees it go up and come straight back down. So the x motion afterwards is also 0. It's just coming straight back down. So ux, this is afterwards, ux is just equal to it's equal to 0. And p franc x afterwards is also equal to 0. It's mu. So the change in momentum is 0, which is good. Change in momentum of franc in the x is equal to 0. Okay, which is okay right there. Now let's look at the y direction right here. What's u franc in the y direction? Well, he's just throwing it straight up at u naught. So it's just u naught. So u naught in the y is just u naught. Which means we plug it into here to get the momentum. P franc in the y is equal to m u naught. Okay, and then after the collision, he sees the ball coming straight back down at u naught. So u in the y would be minus u naught. And the momentum, franc in the y afterwards, would be m times this. So it'd be minus m u naught. And the change is always the final minus the initial. Minus mu naught minus another mu naught is minus 2 mu naught. So the change in franc in the y is equal to minus 2 mu naught. Okay. Now it doesn't have to be 0. All we have to care about is when we add them all up down here, add them all up, the change in momentum in the system, this better be equal to 0 if you want to be conserved. Okay, so now we've got to go over and say, what does Frank say Mary's x motion is right here? Well, what are we looking at? We want to know what Frank sees Mary's x motion to be right here. This is what Frank sees there's Mary's x motion right there. So we're going to come in and we plug in ux equals, he sees the x velocity as ux prime. Well, what does Mary say her x motion is? Well, she's throwing the ball straight down, so Mary's going to say ux prime is 0. She's just throwing the ball straight down. So this is 0 plus v, which is just v, all over, but u was 0. Both of these two were 0, so you can just get that all out of the way. And so you just get v over 1, which is just v. So this is just over 1, which is just v. Which is just v. So ux is just v. That means the momentum of Mary in the x is m times this, which is mv. Okay, after the collision, right here, what was the x motion afterwards? It's still the same thing. It's going up this way. Mary, it's not moving relative to Mary, so it's still mv. So this is ux is still v naught. It's positive. It's going to the right. Momentum of Mary in the x is still mv. Sorry, we said that was v, not m. We said that was v. And so the change, that minus this is 0. So the change in the momentum of Mary in the x is equal to 0. Then we just have one more to do, the y. What does, I guess we can do it right here. What does Frank see Mary's y motion to be? Well, then we're just going to plug into this. This is what Frank sees Mary's y motion to be. So again, ux prime was 0, so this is gone. We just have 1 in the bottom. So we get uy is equal to uy prime. Well, what was uy prime? that was just minus u naught. And then we have the square root of 1 minus v squared over c squared. Okay, so that is the speed right there. So it's uy is equal to minus u naught times the square root of 1 minus v squared over c squared. The momentum would just be m times this, so momentum of Mary in the y would be minus m u naught square root of 1 minus v squared over c squared. Now, what does she say? The speed, what is the speed afterwards? Well, the speed down is the same as the speed up. It's just plus right there. So uy is the same as it was coming down, but now it's going up, so it's plus. U naught square root 1 minus v squared over c squared, and the momentum you multiply it by m, so you get pm in the y is equal to m u naught square root 1 minus v squared over c squared. And now we do the difference. This minus this is two of these because you're subtracting off a negative. So the change in the momentum is equal to 2m u naught times the square root of 1 minus v squared over c squared. Okay, so now if we add these up, do we get 0? And you can see right now that we don't get 0 because this is just minus 2m u naught. This is not a minus 1. If this were minus 1, then they'd be equal, but this is not minus 1 right there. So it looks like momentum is not conserved in Frank's frame. And if it's not conserved in Frank's frame, it's probably not going to be conserved in Mary's frame either. So it looks like momentum is not conserved, Boy, that makes it tough. Because if momentum isn't conserved, this momentum was the bedrock of all of physics for collisions right here. What are we going to have to do? To handle collisions if momentum is not conserved? Well, maybe what we should try to do is come back to here and maybe say, can we change the definition of momentum so that it is conserved? Right here. So maybe we'll go back and just say, well, let's just see if we can change the definition. Now we could just keep trying different things, plugging them in until we get a 0 there. But I'm just going to make a wild stab at one right here. I'm going to say, well, why don't we try P is equal to mu. You know it had to be close to that because that's what we had before. Now you might say, well, wait, why don't we just put in something like the square root of 1 minus v squared over c squared? Well, it can't be this because we have to change the definition just within Frank's frame. That v is only the speed between Frank and Mary. We need to change it even irrespective of Mary right here. So let's try something different. Instead of v squared, what I'm going to try is u squared. Let's try u squared because I know if an object's not moving, or if an object's just going really slow, then this should be close to 0 and we should just get what we had before. So it's not a v I'm going to divide by, it's u, right? The square root of 1 minus u squared over c squared. Remember, this is a vector, so u squared is actually ux squared plus uy squared plus uz squared right here. And so if we just wanted to get the x component of momentum, that would just be mux all over the square root of 1 minus, and then here you'd have to put all three of ux squared plus uy squared plus uz squared all over c squared. And y, you'd put a y there, z, you'd put a z there, but this would stay the same. So let's just see if that works right there. So if that works, maybe we'll just put the changes. I won't redo all this. We'll just make the changes here. What needs to change? Well, the only thing that changes is every place where we got the momentum. Well, if the momentum is 0, it doesn't change at all right there. But right here, it is going to change. It's just going to be divided by the square root of 1 minus, well, what was the total velocity of Frank? Well, remember, for Frank, ux is equal to 0. We don't even need to worry about uz. There's no z here. And uy is u naught. So when we look at when we add up their squares, it's just u naught. So this is just going to be 1 minus u naught squared over c squared. Okay, and the same thing I get over here. This is the square root of 1 minus u naught squared over c squared. And so when I take the difference, this is still going to be the square root of 1 minus u naught squared over c squared. Okay, now we have to go into this next one right here. This one right here is now going to have to be divided by, all momentums are now divided by the square root of 1 minus, now this is going to have to be the speed that Mary's ball is moving with respect to Frank. Remember, it has both relative to Frank. We said ux was this, we said uy was that. So the speed we have to put down below, u Mary squared, is actually this squared plus that squared. It's v squared plus this squared. Well, if I square that, that's u naught squared 1 minus v squared over c squared. So that's what I'm going to have to plug in because it's the x plus the y squared. Okay, so I'm going to leave it as just u Mary squared over c squared. But that's what u Mary squared is. Now this other one is still going to be the square root of 1 minus u Mary squared over c squared. And now when I do the difference, oh, that's nice. I don't need to plug all that in because this is the same as that. And when I subtract it, I still get 0. So it's still 0, even though that's different. Okay, and now we just have to do the last one right here. Here, we get uy is this. Over here, we have to put in divided by the square root of 1 minus u Mary squared over c squared. Again, because it's Mary's from Frank's perspective, and again, it's this. Over here, we get the same thing, square root of 1 minus u Mary squared over c squared, which means we get the same thing over here, which is the square root of 1 minus u Mary squared over c squared. So now I just want to see if this plus this equals 0. Well, so let's plug in right here. So I just want to know if, I'll put this term first, minus this equals 0. Well, you notice I can factor out some stuff, the 2m u naught. So the change in momentum, the total change in momentum is this plus this. But I'm going to factor out the 2m u naught. And then we get, I'll put this term first, we get the square root of 1 minus v squared over c squared. The square root of 1 minus v squared over c squared. And we get down below is the square root of 1 minus um squared. I think I'll plug in my um squared, which was this. V squared plus u naught squared, v squared plus u naught squared. So we get v squared plus u naught squared, 1 minus v squared over c squared, divided by c squared. Okay, so that's this term minus, well, plus this term. So it's going to be a minus because I have a minus 1 over minus 1 all over the square root of 1 minus u naught squared, 1 minus u naught squared over c squared. Okay, now we should be able to see, I'm going to take this term right there, and let's just bring it out. I think I can simplify this thing right there. You notice, actually, I'm even going to take out the 1 too. Well, we're going to take out everything inside that square root. We're going to take all that right there and just work on that for a second. You'll notice right here, what do we get? We get 1 minus v squared over c squared. Then I get minus, we multiply this thing through here, it's minus u naught squared over c squared. And then the last term, minus is plus v squared u naught squared over c to the 4th. So it's plus u naught squared v squared all over c to the 4th. So I just multiplied all that out right there. Now, I don't know if you can see, but that looks like it's factorable. What I'm going to do is, let me rewrite it. 1 minus v squared over c squared minus, I'm going to pull the u naught squared just out of these two terms, u naught squared, and we're left with 1 minus u naught squared over c squared. I'm going to factor that out, and this becomes 1 minus v squared over c squared. Or, I've got these 1 minus v squared over c squared, 1 minus v squared over c squared. I'll factor that out. So this is 1 minus v squared over c squared times 1 minus u naught squared over c squared. So that's what everything in this blue did right here. It just came down to that. Now you'll notice that the square root, this term and that term are going to cancel. And so I'm just going to be left with 2m u naught, 1 all over, the only thing I got left is this term, 1 minus u naught squared over c squared, minus that term, 1 all over the square root of 1 minus u naught squared over c squared. Heck, that gives me 0. Gives me what I wanted. So if I change the definition of momentum to this, then it's conserved in Frank's frame. Now I'm not going to go over, you could do this all for Mary's frame and it will be conserved in Mary's frame too. If you want something to do, it's probably good practice just to work that out. Now, I should tell you that if you look at old books, old modern physics books, that's an oxymoron. If you look at an old modern physics book, you'll notice that they're going to define momentum this way. P is equal to mu, but they're going to say m is equal to m naught all over the square root of 1 minus u squared over c squared. New books, they're going to say no, m is just m, and momentum is mu all over the square root of 1 minus u squared over c squared. They're identical, but this is when they first started out, they were thinking of just saying mass was a variable quantity like this. No. When we say the mass of an object is something, like the mass of an electron, that is the mass of the electron right there, even no matter how fast it's going. If you use this, you'd say it's changing. No, we would say the momentum is what's changing right here, but we're going to keep mass as mass right here. So So, you can tell if you have an old book. We're not going to use this method. We're going to use this one over here. Now, since we have this equation right here, you notice if you were to plot it out, P versus U, this is U and that's P, you notice without this, it's just a straight line right here. So it's just kind of goes like that. But we can see that when U gets up to the speed of light, you're going to get an asymptote. So really what it should look like is like that. That's what it's going to do. And you can see that since we defined F as the rate of change of momentum, right over here, even if you keep applying a force right here, and you keep giving this thing more and more momentum, even if for an infinite amount of time, if you give this thing more and more momentum, so that means this way is going up, you'll notice you'll never get to the speed of light. So even a constant force on an object forever will never get it up to the speed of light. That's what we say, you could never get up to the speed of light because you'd have so much momentum that you just don't have any force to get it going any faster. So it takes an infinite amount of force to get it up to the speed of light. That's why we can't even get an electron up to the speed of light. It would take an infinite amount of force. Okay, and now we can go back to what force was. And remember, since force is just the derivative, it's just dp dt, now we have a definition of force, because we could just take the derivative of that with respect to time, right here. So, and we'll do that on, actually on the next one right here. We'll just take the derivative of this to get the force. But now, this is the first change that we've had if we were, where we said 4A was classical mechanics is now different. So if you went back, this is the first spot, because you never went through Frank and Mary and classical mechanics. But this is nothing to do with Frank and Mary. Just if you see an object moving, that's the momentum. Okay, and that's why, just forget, this is a U, it's not the V. So this isn't gamma right here. Gamma has the V in it. Okay, so we'll talk about force next time.